Hello and welcome to the 8th video in lesson 1. Here we will have a short overview of the four main analysis methods for the demand analysis in LEAP. In this video we will quite shortly look at the four main methods for demand analysis in LEAP, which means the four main ways that you can input data and how to structure that input with the different data types. Then we're also going to look at the four different methods and for the overview and also discuss briefly their differences. In the further videos for lesson 1, we will discuss the first two methods, which are the simple methods, and then in lesson 2, later on, we will discuss the two other methods which will require more explanation and data. For the demand analysis in LEAP, there are four main methodologies. Total energy method, energy intensity method, which can be split into two, but they are very similar and also just counting as one as they use the same kind of data and for similar purposes. Stock turnover, the normal way, and transport stock turnover, which is specialized for road transport. The simplest of the analysis methods in LEAP for demand is total energy. Total energy is just for when you have no other data than just your energy consumption. So very simply, it is when you have a sector and you predict the energy consumption directly for that entire sector. It is usually mean you have nothing else in terms of data than an energy projection forecast, and it only has this one parameter, which is energy. So that's the parameter is energy directly. This is this is only to use when you have really nothing else and you have a quite simplified sector or subsector. As a slightly more complex methodology for analyzing energy demand, we have the energy intensity method. The energy intensity method works with two parameters, specifically the activity of the demand and the energy intensity, EI. Those multiplied together equals the energy demand. What that means in a practical way could be, for instance, housing, where you have defined the energy demand as a multiplication of the activity. Could be the total square meters of housing in your area, multiplied by the energy intensity of how much it would take to heat per square meter of housing. You can do the same thing for cooling. You can do the same thing for industrial processes as well, where you have maybe the energy intensity of producing cement multiplied by the activity of how much cement needs to be produced. This is a very common method that is used in LEAP. The slightly diverging from the energy intensity analysis method is the useful energy intensity method. It is under the same umbrella, but here I am defining it just by itself because while it is functionally similar in LEAP, it does distinct in a certain way. With the useful energy intensity method, it uses both the activity and intensity just as before, but the energy demand is then also multiplied by the efficiency of a certain technology. So you have the activity, that could be number of square meters of housing, multiplied by the energy intensity, that could be the level of insulation that the housing has that causes it to have an energy intensity of saying how much energy is actually needed to heat per square meters, and then multiplied by the efficiency of the of whatever heating technology that is being used. That means you have three parameters you can adjust. So you have both the activity, like how much housing is there of this certain kind in your system. What is the energy intensity? That could be adjusted by adding insulation or shadow effects. And what is the efficiency of your demand need? If it's heating, you could exchange oil boilers to heat pumps and get a vastly different energy efficiency for that technology and therefore change the energy demand. In something like industrial processes, instead of focusing just on cement, you can focus on a part of cement where you're saying that we need a certain amount of limestone to be crushed. That's the activity that has a certain energy intensity. You need energy per ton of limestone to have crushing. Whether you do that with electricity coming from grid or used by a generator-based system has a wide difference, and that also affects your energy demand. Then we also have stock turnover analysis. This is most commonly used for consumer products such as refrigerators, TVs, washing machines, and so on, that has a market, open market to them. And what's special about this is it very much depends on the generation or the year that the product was bought. So that means if you buy a product in 2020, how will it act throughout its lifetime? Will it degrade in efficiency? Will it how long is it projected to averagely last? That is used to profile, and then you can forecast the energy forward. The special thing about this is that it's not and it's no longer averages that's being used. It's an actual generation. We'll look a lot more into that, especially with transport bill, which is the next thing. The important thing here is if you have something that gets regularly exchanged in your system that develops quite rapidly in terms of their energy efficiency or energy consumption, this is the methodology to use. So if you take something like the Japanese policy for consumer electronics, where the most efficient standard or product on the market today has to be the standard in a minimum requirement in 5 years, this is a way to do that. It also you can also adjust the policy saying, what if you now try to adopt a policy of a high efficiency refrigerators in 5 years, or for that matter next year, and seeing how that will change over the lifetime, but it's no longer an averages, so you can see how long the lag effects are. So if you convert everything to high efficiency products tomorrow, it will actually take a number of years before the total stock of products in your country is at the same efficiency, and it will also take a number of years before you're even half that way. So this is a good way to project that. Then we also have another stock turnover analysis, which is exactly the same thing, but it just specifically meant for cars or other road vehicles. So here you can define your fuel economy, the efficiency for vehicles, along with the year was purchased, the profile of the survival profile of the vehicles, or when they retire in terms of statistics, how motors degrade over time, and you can do that per year. The driving force here, or the driving input here, is the sales of different vehicles per year. So if you have a certain vehicle stock now in the system, and you decide that you should have a number of sales of a stock or sales, for that matter, of EVs in 10 years, for instance, like you want 50% EVs in 10 years, well, you can then use this system to also adjust to see how much sales do you actually need, sales share of EVs would you need to go towards these 10 years. Because if that is too short or not rapid enough, you will see that you will not succeed in your stock. We'll look more into, in the next video, the two simpler versions, and in lesson 2 we'll look into stock turnover.